is there a general formula for this kind of integral? The integral of dx over x to the power of n plus 1. Well, I'm pretty sure that we know how to solve much simpler versions of this integral. For example, the integral of 1 over x plus 1, which is the case when n equals 1, right? dx. And we know this integral simply equals c plus the natural log of x plus 1. This is simple, right? Child's play. So what about for n equals 2? Okay, we have 1 over x squared plus 1 dx, and we know it is the arctangent of x, of course, plus c. All right, so we see natural log arctangent doesn't seem to have any meaningful connection. Let's try another one that is quite familiar too, which is the integral of 1 over x squared minus 1 dx. Well, how do we deal with this integral? Well, I hope you remember the basic technique is that you split the denominator into two terms like this. Integral of dx over x minus 1, x plus 1. Okay, where 1 and minus 1, I mean, this is x minus 1, right? And this is x minus minus 1, right? And 1 and minus 1 are simply the two solutions, to the equation of the denominator equal to 0, right? So we factorize the denominator, and then we try to split it into two integrals. The integral of a dx over x minus 1 plus the integral of b dx over x plus 1. And then we try to solve for a and b in terms of 1 and minus 1. Maybe they will turn out to be 2, 3 or something. And then this will simply be equal to a times the natural log of x minus 1 plus b times the natural log of x plus 1, and then plus c. Okay, so the whole problem is to find a and b. Okay, and how do we find a and b? Well, the trick is to equate the integrand here and the sum of the integrand here. So we have 1 over x minus 1, x plus 1 equal to a over x plus 1 times b and x plus 1, right? Like this. So how do we find a? Well, the trick is you multiply both sides by the denominator of the a term, which is x minus 1. And you multiply by x minus 1 here, and you multiply by x minus 1 here. And then you let the whole thing, you let x approaches 1, which is the solution here, the solution of this equation here. And what do you see? You see that, well, first, before you take the limit, the x minus 1 term here will cancel. And so will they here. However, it will remain here. There's nothing to cancel in the b term. So when you take the limit, nothing happens for the left-hand side. It will simply become 1 over 2, right? And for the right-hand side, the first term is the remaining a. But for the second term, this term approaches 0. And the denominator is simply 2, right? So whatever it is, it will be 0. So we found a. And then we do the same trick for b. The only difference is, this time we're going to multiply by what? By x plus 1, right? X plus 1, and x plus 1. And then we will let x approach minus 1. Okay, so by doing that, you see here, the x plus 1 term will cancel with the same term at the bottom. And then we have what? Minus 1, we have 1 over minus 2. Okay, and here, this term will vanish. And the only term left is b, right? So x plus 1 and x plus 1 simply cancels, okay? The limit doesn't do anything. And b is left as minus 1 over 2. Okay, and that's how we find a and b, and we solve the integral. So this is a very standard technique for solving integrals, that you can factorize the denominator of the integrand into multiplying terms with very specific solutions like this. Okay, so that's how about 1 over x cubed plus 1 dx. Okay, so now the story is kind of complicated because you cannot factorize into 3 terms, right? Because there's only one real solution, which is -1, right? -1 is the only one real solution. And you can either say there are 2 more imaginary solutions, or you can say there is a how to say non-solvable quadratic term, right? And then we have to proceed pretty specifically in a way to deal with the non-solvable quadratic term. But in this video, we will try to figure out a general formula for this integral, regardless of what n is. Okay, it can be 3, 4, 5, whatever, we don't care. And of course, as you may have guessed, we will stick to the thinking that every sort of denominator of this kind can be represented as a product of how to say linear terms, like x minus something, x minus something, and x minus something, and there will be n terms of such terms. However, as you also may have guessed, we will not stick to the situation where there will be a non-solvable term somewhere. We will assume that we can always factorize the denominator into multiplying terms. And why is that? Because we will deal with this integral in the complex numbers set. Okay, so in complex numbers, such equations will always have n different solutions. Okay, so there will not be any non-solvable terms. They will always be separable into multiplying terms. That being said, so now let's set up our how to say framework to solve this integral. So we start with the integral of 1 over x to the power of n plus 1 dx. Okay, and we will let's set it equal to the integral of 1 over x minus, I will say, x1, x minus x2, dot dot dot, x minus xn dx. Okay, so what are these x's? x1, x2, and x3, and xn, and so on. They are the distinct solutions. Okay, they are the distinct solutions to what equation? To the equation x to the n plus 1 equals 0. Okay, they are the distinct solutions. So what do we do next? Suppose we can factorize it into this form. So the next step is to transform it into a sum. Okay, so it will be a sum of b1 over x minus x1 times b2 over x minus x2, and then use sum all the way into bn over x minus xn, and of course dx, right? So there will be 2 steps. The first step is to find the solutions to this equation. And the second step is to find the b's, the coefficients b in this form. Okay, and of course the next step, the final step, is easy. This will turn out to be a sum of natural logs. Okay, so of course we have a constant, don't forget that, and we have a sum of bi times the reciprocal of x minus xi. I'm sorry, this is a natural log. Okay, natural log of x minus xi. And the sum goes from I equals 1, right? I equals 1 all the way to n. Okay, so basically this is our general solution. is very simple now because we haven't done anything with it. We haven't found the exact form of xi, and we don't know what bi is, right? So we will break it down. So firstly, we will deal with bi first. Okay, let's find bi. How to find the coefficients of the sum. So, well, we basically we turn back to the same process that we found a and b here. So the thing is to equate this integrand with this integrand. Okay. So what do we have? We have 1 over x minus x1, x minus x2, dot dot dot, x minus xn, and there will be a shorthand notation for this. It is the product symbol, which is a large capital pi letter from I equals 1 to n of x minus xi. All right. And what will it be equal to? It will be equal to this term, which is, I will write it again, b1 over x minus x1 plus b2 over x minus x2 plus dot 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 plus bn over x minus xn. Okay, and there is also a shorthand for this. It is a sum, of course, from I equals 1 to n of bi divided by x minus xi. All right, so we have a product being set equal to a sum. And our job is to find the bi's. Okay, so the same trick will be applied. So suppose we want to find b1. Let's say we want to find b1. So what do we do? Okay, what do? We will multiply b1's denominator to both sides. Okay, so we will multiply it here, x minus x1, whatever x1 is. We don't care about that. Okay, I'm sorry, I need a reciprocal thing here. Sorry about that. Okay, and then we'll multiply here, x minus x1. All right, x minus x1, x minus x1, all the way to here. Okay, and then what do? We would take the limit. Okay, we would take the limit as x goes to x1. All right, so before taking the limit, we need to notice that these terms have already cancelled. They won't be affected by the limit, in a sense that there will be no zeros up top or at the bottom, okay, because these solutions are distinct. So x1 is guaranteed to be different from x2, so we don't need to worry about that. So all the zeros are taken care of before we're taking the limit, okay? So also the same things applies to here. We don't need to care about the zeros when taking the limit because they're already cancelled, okay? So now we take the limit. And this term will approach a constant, right? It will approach a constant because when you sub in a constant minus a constant times a bunch of constants, you will get a constant, okay? And look at the sum. All of these terms will become 0 because they are multiplied by 0. So all of these terms vanishes, okay? All of those vanished. And the only surviving term is b1, So all we are left with is b1. And that constant is nothing but b1. Okay, so we have a general formula for b1. b1 will be the limit, okay, of x approaching x1 of x minus x1 divided by the product of I equals 1 to n of x minus xi. And this is the very general formula for b1. And of course, we can do the same trick for b2, b3, b4. So we can also write as bi. Okay, we can write as bi. And of course, if you don't want to be confused with the dummy index of the product, you can change the dummy index here to j or something. Okay, it says j or whatever. You get the idea, right? J in j. Yeah. So we have this formula for the b's, right? And what are the b's represented in terms of? They're represented in terms of the xi, right? In terms of the solution to this equation, right? So now our next step is to solve this equation to find what is the general formula for their distinct solutions, okay? So let's start with a simpler version of it, okay? Let's start with x plus 1 equal 0. So we know for sure x is equal to minus 1, okay? That's it. It's the end of the show. X equals minus 1. So what about x squared plus 1 equals 0? Well, this may seem a little tricky, which is x squared equals minus 1. Well, if you're familiar with the complex numbers, you will not panic at all. And if you are unfamiliar with complex numbers, I think the following part will be pretty hard to keep up if you're not familiar with complex numbers. So let's suppose you are familiar with complex numbers, okay? So we know there are two distinct solutions to this equation, which is x equals I, which is the imaginary unit, or x equal minus I, right? We still have two distinct solutions that satisfy this equation. So no stress about it. So what about x cubed plus 1 equals 0? All right, so we have x cubed equals minus 1. And yeah, the first thing that comes to mind is, of course, x is minus 1 itself, right? Is there any more? Well, yeah, of course, because we are dealing with the complex numbers, so there will be two more distinct complex solutions. So how do we find it? How do we find it? Well, there's a very nice thing that you can make use of. It is the Euler formula. It is the Euler formula, okay? In polar form, not in trigonometric form. I mean in polar form. So what you have is that how to say, minus 1, okay, minus 1 can be represented as e to the I pi, right? E to the I pi. Or more generally, it can be e to the I pi plus 2 pi, right? Or more generally, k2 pi. Okay, I'm running out of space. I should write it somewhere here. Okay, minus 1 can be written as e to the I pi or e to the I of pi plus 2k pi or k2 pi, whatever. But you get the idea. You get the idea, right? Because adding 2 pi to the argument of a complex number doesn't change the number at all. But we can do it for the sake of generality, right? So how to interpret this formula on a complex plane? So we have the unit circle on a complex plane, right? This is the imaginary axis. This is the real axis, okay? So on the real axis here, we have the real unit 1, or it is I e to the I times 0, right? Here is our familiar I, which is e to the I pi over 2. Okay, so basically you take where you are, the angle of your imaginary, I don't know, the angle of your complex number arrow, and you put it here, right? Pi over 2, 0. Okay, so once you get here, you will be e to the I pi, right? Because you are at pi on the unit circle. And here you are e to the I 3 pi over 2. Okay, or you can be e to the I minus pi over 2. They're the same thing. All right, so this is the unit circle on a complex plane. And where are we? Where do we want to be? We want to be minus 1. Okay, so we are here. We are here. Minus 1. And now we need to find complex numbers z, so that when it is cubed, it lands on this spot on a circle. Okay, so in complex numbers, what does squaring, cubing, or the fourth power, what do they do to the numbers itself? So I suppose that the magnitude of x, the modulus, is equal to 1. Okay, so it makes the story much more simpler. Okay, so x squared is simply multiplying 2 to the argument of the number, and multiplying by 3 and multiplying by 4. It is that simple. Okay, for example, if I have a complex number x here, and then I want to find x squared, so basically I will double the angle, and here it is, x squared. It is that simple. Okay, what is x to the fourth? Well, you multiply the angle by 4. 1, 2, 3, 4. Let's say x to the fourth will be here. That is the basic idea of exponentiating a complex number to an integer. Okay, I mean, it also works if it is not an integer, but you get the idea. So now, how do we find a number that when cubed, it lands on -1? So we work backwards, right? We take the argument of -1 and we divide it by 3. And we know where our x should be, right? So we have the angle pi here. If we divide it by 3, we get pi over 3. Okay, pi over 3. And where is pi over 3? It's here, right? Yeah. And this is our first solution. I guarantee that when you multiply this angle by 3, okay, 1, 2, 3, and you will land on -1. Okay, so we have the next solution here, x equal e to the I pi over 3. Okay, so what next? What is the other solution? So, we kind of run out of intuition here. I mean, you can go on with intuition, but it takes a while, so we will use math instead. Okay, so we know that e to the I pi plus k2 pi is equal to x cubed, and then we will find simply what x is by dividing the whole argument by 3. So it is e to the I pi over 3 plus k2 pi over 3, right? So let's say when k is 0, so we have this bad boy here, which is right here, right? K equals 0. So what if k equals 1? What if k equals 1? Well, k equals 1, you keep winding the angle by another 2 pi over 3, and you land where? Exactly here. Okay? Okay? You add another 2 pi over 3, and you get exactly -1. So the real solution here is for k equals 1. Okay? And what about k equals 2? So you add another 2 pi over 3. And where do you get? You will get here. Okay? Yeah. And you know where that is? That is e to the I don't know, just plus another 2 pi over 3 to it. You will get 4 pi over 3. Am I right? Maybe 5, right? 5 pi over 3. Or simply, it is e to the I minus pi over 3, because you can also count the angle backwards from here. Okay, so we have x to the I, e to the I 5 pi over 3. And this is for k equals 2. All right? So you can proceed this, this process with any number on a power. Okay, for example, if you want to solve x to the fourth equal -1, so you simply do what? Well, -1 is e to the I times pi plus k to pi, and then you divide the whole angle on the exponent by 4, so you get x equal to e times I pi over 4 plus k 2 pi over 4. Okay, and then you have 4 distinct solutions. X when k equals 0, k equals 1, k equals 2, k equals 3. Okay, and you don't need k equals 4, because it will loop back to k equals 0, and you can see this for yourself. Okay, so generally, when we have an equation of the form x to the n equals -1, okay, I mean, it is the same thing as x to the n plus 1 equals 0, right? And we will have the general solution of x sub k, which is the kth solution, is e to the I pi over n plus k 2 pi over n. Okay, where k can be anywhere from 0 to n minus 1. Okay, good enough, right? So just to simplify things a little bit, this is simply e to the I pi over n, and we have 2k plus 1, right? Just to simplify things a little bit. And instead of letting k run from 0 to n minus 1, you can also let it run from 1 to n, whatever you like. It is the same thing, because you shift everything 1 unit forward. It doesn't change anything. So I prefer writing from 1 to n. It seems a little neater. Okay, so k belongs to the interval of 1 to n. Oh yeah, so now we have the exact formula for the solutions to the equation when you set the denominator equal to 0. Okay, so now let's put it all together. Okay, we know what these solutions are, and we know how to find the b's in terms of the solutions. And basically, we have done the big 2 steps to derive the general formula for this integral. And yeah, let's put it all together. All right, so first we have our original integral here, x to the n minus 1 dx. Okay, now we are going to factorize it, right? We are going to factorize it, and it will be the integral of dx over the pi. It is the product of I equals 1 to n. Okay, and x minus xk. All right, okay, let's use k for the index. Yeah, and what is xk's? What are their full form formulas? Okay, let's plug them in. It will be kind of ugly, but let's do it. Dx over the pi, product of k equals 1 to n, and then x minus e to the I pi over n 2k plus 1. Yeah, that's it. Am I right? Yeah. Okay, and then what? And then we will turn it to the sum. It will be a sum, right? It will be the integral of the sum of I. Is it I or k? Let's say k. Okay, k equals 1 to n of bk divided by x minus e to the I pi over n of 2k plus 1. All right, and how do we derive bk? Well, we know is the integral. Well, let's turn it to natural log. Okay, let's perform the integral. Here's the sum k equals 1 to n of bk times the natural log of x minus e to the I pi over n of 2k plus 1. Right, so now let's plug in the ugly formula for the b's coefficients plus c. Okay, so it will be the sum k equals 1 to n, and now we'll put a big bracket for b. Okay, I'm dealing with b only. So what is b? B is the limit of x, and let's solve for bk. Okay, bk. So x will tend to xk. All right, and what is xk? Xk is just this guy right here. All right, so x tending to e to the I pi over n 2k plus 1. That's our limit. The limit of what? Of x minus this guy, right? I pi over n 2k plus 1 divided by the product, the big product, k equals 1 to n of x minus e to the I pi over n of 2k plus 1. Yeah, and that is b. Okay, and then we will have the natural log of x minus this guy again, and plus c. Okay, so one final touch, so that we don't accidentally confuse the actual variable of the function x and the x in the limit. So I will change all the x's in the limit to u. Okay, to u. So it is just for the sake of doing the limit, so you get a number out of it. It is not the variable of the function. Okay, yeah, and that is pretty much it, right? And also for the Yeah, I think we nailed it. We got it. Yeah, this is the general formula for 1 over x to the n plus 1 dx. We got it. Yeah. So, of course, in mathematics or in physics or I think in any mathematical science, when we derive a formula, the first thing we're going to do is that we should put it to a test, right? We should put it to a test to see if it can give the right answers in specific circumstances. So first of all, we expect if n equals 0, if n equals 0, right? We would have the integral of 1 over 2 dx, and it will be, x over 2 plus c. And let's see if our very long formula can give us x divided by 2 plus c, right? So now, for n equals 0, we see that our sum doesn't work because n is the capping of the sum. Well, yeah, I think summing from k equals 1 to 0 doesn't make much sense, right? Well, this is pretty simple to understand because the whole thing is based on setting the denominator equal to 0, and then we find the solutions. And of course, 2 equal to 0 doesn't have a solution. So the special case of n equals 0 is understandably not reproducible by our formula because it is not part of our general assumption that the denominator can be set equal to 0. Okay, so next, let's give it a pass here and let's try n equals 1. Okay, for n equals 1. So we have the integral of 1 over x plus 1 dx, and we expect it to be the natural log of x plus 1 plus c. Okay, and let's see if our formula can work it out. Okay, now we will sum all the way from 1 to 1. Pretty simple, huh? From 1 to 1. So we have only one term. All right, only one term. So first of all, what we're going to do? What we're going to do is we're going to set n to 1 everywhere. Okay, n equals to 1 here, n equals to 1 here, n equals to 1 here, and n equals to 1 here. Okay, and what about k? K starts with 1 and ends with 1, so k everywhere is also 1. So k is 1, 1, 1, 1, and we have only one term. Okay, let's see how it will turn out. Okay, so it will be equal to the limit of u tending to e to the I pi. 2 times 1 plus 1 is 3. Okay, and what about this guy here? U to u minus e to the I pi times 3 also, right? And the product. Okay, the product is also from 1 to 1, so we have only one term in the product. And what is it? It is u minus e to the I pi 3. All right, then we have the natural log of x minus e to the I pi times 3 plus c. All right, and this limit is trivial. It is 1, of course. Okay, and what is e to the I 3 pi? Okay, so let's see where we land with 3 pi. We have 1 pi here, 2 pi's here, and 3 pi's here. So e to the I 3 pi is simply 1, right? So we have the natural log, sorry, minus 1. Okay, so natural log of x minus minus 1 plus c, and the whole factor up front is only 1. So yeah, we got what we wanted, right? Exactly what we got. So the formula works for this very simple case. Okay, so now let's put it to the next test where we will have n equals 2. Okay, I will delete this here. Oh yeah. Okay, so now let's go to the next case. N equals 2. For n equals 2, so we have the integral is equal to 1 over x squared plus 1 dx. Okay, and we know it is the arctangent of x plus c. So now we see a very big problem. We have a whole new kind of function here, the arctangent. However, in our formula, we only have natural logs. Okay, whatever this term is, it is simply a number, and we have a linear combinations of natural logs. And how do we end up with the arctangent? Well, let's forget that for a moment. Let's just apply our formula and see what we get. Okay, and then we will try to figure out how do we make the arctangent emerge out of nowhere. All right. So now we have n equals to 2. So there will be two terms. Okay, there will be two terms. The first term is the limit, right? We always have the limit up front. The limit of u tending to e to the I pi divided by n. So n is 2. We got 2 here. Of 2k, right? K will run from 1. So the first term k is equal to 1 plus 1. Okay, of what? Of u minus e to the I pi divided by 2 times 2 to the 1 plus 1. All right. And next, what do we have? We have the product, right? We have two terms. So there will be two terms here. That's for sure, right? The first term is the same. 2 times 1 plus 1. And what is the next term? The next term is where k equals 2, right? So u to the e I pi divided by 2, 2 times 2 plus 1. All right. And then we have the natural log of, let's put it all in a bracket here. Okay, we have the natural log of x minus e to the I pi divided by 2 times 2 times 1 plus 1. And yeah, plus the second term. This is crazy ass long. U to the e I pi divided by 2 and 2 times 2 plus 1. Okay, which is the next solution. And u minus 2 times 2 plus 1. And then we have the same thing here. 2 times 2 plus 1. U minus e to the I pi divided by 2. 2 times 1 plus 1. Well, I should have written it in the same order, right? Yeah, maybe I should have. 1 and 2. Close the bracket, and we have the natural log of x minus e to the I pi divided by 2 times 2 times 2 plus 1. Yeah, and plus c. So what are we going to do? Well, the first thing we got to see, and of course we're going to see because it's the whole point of the deriving the formula, right? So we have this term completely cancels with that. This term completely cancels with this, okay? And then simply we put this into here, and we put this into here. Sorry, into here, right? Yeah. So we're gonna have, what are we gonna have? We're gonna have 1 over e to the I pi divided by 2, and what is this? I'm tired of this. It's 3, right? 3 minus e to the I pi divided by 2, and what do we got here? 5, right? Yeah, and then the natural log is x minus e to the I pi over 2 times what? Times 3. E to the I pi over 2 times 3. Okay, plus the second term, which is 1 over, put it here, e to the I pi over 2 times 5 minus e to the I pi over 2 times 3. Cool? Yeah. Natural log x to the minus x minus e to the I pi over 2 times 5 plus c. Okay. So the good thing is we realize that this term is actually the minus of this term. Okay. And let's do this. What is this? Okay. So we need to pull out our unit circle again. We need to pull out our unit circle again. And e to the pi over 2. Pi over 2 is here. Right. And where's 3 pi over 2? Here's pi over 2, 2 pi over 2, and 3 pi over 2 is here, right? 3 pi over 2 is here. So we have minus I, okay? Minus 5 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and 5 pi over 2. Am I correct? Yeah, 5 pi over 2 is here. And Wait, I think we're wrong. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2 is here, 5 pi over 2 is here. Sorry. So yeah, this is I, right? 1 over this boy, natural log x minus, what is this? This is minus I, all right? And then what do we have here? We have I minus I, right? Yep, times the natural log of x minus I plus c. Okay, are we good here? And now let's simplify a little bit. Okay, well, what is this term? It is 1 over minus 2i, right? 1 over minus 2i. Natural log of x plus I, right? And what is this? 1 over 2i. Natural log of x minus I. Oh yeah, yeah. And let's simplify a little more. We can factor out. We can pull out the 1 over 2i, and we will have this natural log minus this natural log. Okay, so it will be the natural log of the quotient x minus I over x plus I plus c. So yeah, this is our, this is what our formula gave us. And does it equal to the arctangent of x plus c? Let's forget the plus c for now. Okay, we will see if this thing is the arctangent of x. So to do this, we need to, have a bridge, some kind of bridge between the real and the complex. And there will be some very unexpected results relating seemingly different functions to one another. Okay, and we will see through this derivation. So we know that e to the I phi, whatever phi is equal to the cosine of phi plus I times sine of phi, right? So, okay, so we will have e to the minus I phi will be the cosine of minus phi, which is the cosine of phi itself, doesn't change, minus I sine phi. Okay, actually it is plus I sine minus phi, but you can pull the minus sign out of the sign. Yeah. Okay, so you can add the two equations so that the sine terms cancel, and you have the cosine of phi equals to 1/2 of what? Of e to the I phi plus e to the negative I phi. Yeah, and you can minus the two terms, right? So you will have I sine phi equals 1/2 of e to the I phi minus e to the minus I phi. Okay, so now we can divide, and what do we have? We would divide the bottom by the top, okay? And we have I tangent of phi, right? Because sine over cosine is tangent. And this one half and one half will cancel, so we have e to the I phi minus e to the I phi divided by e to the I phi plus e to the negative I phi. Yeah, we have this formula, right? So what are we going to do with it? Well, let's set tangent phi equal to x. Okay. In other words, we have x is the tangent of phi. All right. So let's put it that way. So we have ix. Okay, ix equal to e to the I phi minus e to the minus I phi, like this. Okay. And what do we want to do? We are going to multiply the top and the bottom by e to the I phi. Okay. And what are we going to have? We're going to have, let's call this guy u, okay, because I'm getting tired of writing that guy's full name. Let's call it u, and we will have u squared minus 1 divided by u squared plus 1, and it is equal to ix, right? So now we will solve u squared in terms of x, all right? So we can multiply this guy up, and we have ix u squared plus 1 equal to u squared minus 1. Yep, and we can pull out the u squared. So we have ix inside, and we can throw this guy on the other side. -1 equals to -1. Um, minus ix. Okay, let me check the math. I think I got it. I think I got it right. Yeah. And then we're gonna have u squared is -1 minus ix divided by ix minus 1. Or we can, switch the position of the denominators of the denominator terms, and we can eliminate the minus sign on the top. And this is what we have. To put it a little more, symmetric way, we can write it like this. Cool. Cool. And let's recall what is u squared. Okay, u squared is just this guy squared, right? So it is e to the 2 times I phi. All right. Yeah. So here's the interesting part. Look at this. Look at this. Look. What we're gonna do? We're gonna take the natural log of both sides. Okay. The natural log of 1 plus ix divided by 1 minus ix will be equal to 2i phi. 2i phi. And do you remember what phi is? Phi is the arctangent of x. I'm sorry, I completely messed up here. All right, we should have written phi equals the arctangent of x, right? Yeah. So phi is the arctangent of x. All right, so this is 2i times the arctangent of x. Voila, we have a relation between the natural log and arctangent through the complex numbers. Okay, so now let's put it one more step. So the arctangent of x is nothing but 1 over 2i times the natural log of 1 plus ix divided by 1 minus ix. Yeah, so let's see if we have proven what we set out to do. Oh, here. We have 1 over 2i times the natural log of x minus I and x plus I. Okay, x minus I and x plus I. So we're pretty close. Okay, we're pretty close. And actually we are, quite close. We can divide it by I, or we can multiply by minus I, right? We can multiply by minus I. And what do we get? Natural log of, you see, so the minus I comes in, it becomes minus I, right? And minus I goes with I, you get 1. So x minus I up front. And similarly, you will have minus I, right? And minus I goes with minus I. What do you get? You get minus x, right? Did I mess up somewhere? Did I mess up somewhere? Yeah, I think I got it. But we got a redundant minus sign right here. All right. Can it be absorbed into the constant? Well, I think it can be absorbed into the constant, right? Yeah, I think so. Because this is equal to 1 over 2i of the natural log of x minus I, x plus I, minus the natural log of I, whatever that is just a number, and it can be absorbed to the constant plus c. Yeah, so I think we made our point, right? We proved it. We proved it. So yeah, I think we proved it. If you are still doubting this formula, please try yourself with n equals 3. And whenever you expect an arctangent to come up, you will have to use this formula to relate the natural log to the arctangent. Okay, so yeah, so that's it. This is the formula that we cooked up to solve this infamously difficult integral. Thank you.